bases, how do we measure the strength of a base? In other words, the likelihood of a base to accept a proton. There are two ways of doing this depending on the type of base. For anionic bases, or conjugate bases of acids, we measure their basicity relative to the pKa of the acid. The larger the pKa of the acid, the stronger the conjugate base. In other words, if we have a weak acid, then we will have a strong conjugate base. Out of the acids listed here, ethanol is the weakest and HCl is the strongest. When we consider their conjugate bases, the conjugate base of ethanol, the ethoxide ion, is the strongest and is therefore most likely to accept a proton. Meanwhile, the conjugate base of HCl, the chloride ion, is the weakest and is therefore least likely to accept a proton. But what about neutral bases, such as NH3? We measure their basicity relative to the pKa-H of the conjugate acid of the base. We include the H this time because the conjugate acid is protonated. The larger the pKa-H of the conjugate acid, the stronger the base. That's how we measure base strength, but what about factors which might affect the strength? The key thing to consider is the availability of electrons on the base. These electrons must be readily available to accept a proton. Firstly, let's consider the effects of electron withdrawing groups in this series of bases. As you can see, lower pKa-H values are recorded for bases with electron withdrawing groups. This is because electron withdrawing groups will decrease the availability of the lone pair on the nitrogen, so the base is less strong. Related to this, hybridization can also affect base strength. A lone pair in an sp orbital with increased s character and therefore increased electronegativity will be far less available than a lone pair in an sp3 orbital with less s character and decreased electronegativity. The presence of an adjacent pi system can reduce the lone pair availability as a result of delocalization effects. Take the unconjugated cyclohexylamine and the conjugated aniline systems. Aniline has a lower pKa-H, so it is less basic. This is because the lone pair is delocalized into the benzene ring, reducing its availability for use in accepting a proton. Finally, we are going to look at the effect of increasing substitution on the strength of amine bases in a water solvent. Take this series, NH3, NRH2, NR2H, and NR3. The pKa-H pattern seems strange in this case. It peaks in the middle. So what could be the reason for this? By increasing substitution, electron density on nitrogen increases due to inductive electron donating effects from the alkyl groups. This means the nitrogen lone pair is more available, so basicity should increase as substitution increases. But we must also consider the stabilization of the conjugate acid due to solvation in the water. For the conjugate acids with more hydrogen atoms attached, there is stabilization via hydrogen bonding with water molecules. As substitution with alkyl groups increases, there is less hydrogen bonding and therefore less overall stabilization. Therefore, basicity should increase as substitution decreases. As a result of these two competing factors, the highest basicity levels are observed in the middle of the spectrum, NRH2 and NR2H, where the factors are relatively balanced. Try the quiz to test your understanding of acids and bases.